This was a major scrap reduction Six Sigma charter project when I was working for Rocklin Automotive, which turned into a reliability project for me on a production cell line that was coupled to a 2,300-ton injection molding machine that produced SCR tanks with 8 downstream secondary pieces of equipment. The secondary pieces of equipment comprised of assembly machines in which the main body of the SCR tank had components installed into it by various methods, such as a hot plate. There was 2 seal and leak testing machines and a final function tester at the end of the process. Mean time between failure was 2.4 hours and the mean time to repair was 4.4. What I was able to calculate, the true availability was 70% and the raw throughput yield was 78%. This is the layout of the production cell that had 8 discrete processing operations to it, and this is why I chose to use raw throughput yield and availability as my Y output key performance indicator. This is a stack bar chart that shows the historical frequency of scrap parts for the category it was scrapped under. The trend lines, an indication of special cause, are for select parts and missing operation, which is showing the slope upwards or downwards in its direction, and the intercept, the point at which the line breaks through the y-axis, and the linear relationship between the variables between each week and used to estimate the average rate of change and the overall direction of the data, which was increasing. Ideally, we would like to see the slope of these indicators either be flat or better, going in a downward direction, showing the trends in reduction and not a trend in increase. This is an SAP report that I produced to break down all the scrap single component categories that I have filtered by pump modules. Year to date was $90,000 in this case. In the previous year, 2020, I calculated that we lost $578,000 in process defects alone between the components and plastic resin that the SCR tanks were made from. That's just the cost of material. You could really go down a rabbit's hole if I wanted to by extrapolating all the other costs such as labor, cost of revenue, and the cost of remaking the scrapped SCR tanks. Exported data from SRP, again showing in this spreadsheet the plastic resin to the tune of $58,548 for a 10-month period. The pump module was the most expensive component, averaging $125 each. In 10 months, we scrapped off $253,000 worth of pump modules. The alarm bell should be ringing by this time of all that money going to a landfill. This is an SAP report that I sorted and filtered in an Excel spreadsheet that details the breakdown of all the scrap single component categories, which I filtered by pump module. This is my define phase of the project. I conducted several data collection campaigns from Pareto chart analysis to scrap and defective parts to mean time between failure to mean time to repair. I used the scientific method as an empirical method to uncover causation through observation, questioning, drawing a hypothesis, designing an experiment, an analysis, and coming to a conclusion and sharing my conclusion with everyone else for external review. As I got into this project, it was very clear to me that this equipment was responsible for 80% of the scrap and interruptions to production as unplanned downtime. The line had an availability of 70% on the average. It's here that I had agreed that my key performance Y factors and indicators for this particular project will be mean time between failure and mean time to repair to calculate the true availability of the equipment. And because this production cell had multiple discrete operations, I used raw throughput yield for the quality rate. In order for me to progress to measure, I had to understand which of the downstream processes was causing the most downtime occurrence and for how long. I placed at each workstation a downtime data collection sheet, clipboard, and a stopwatch and trained the operators on how to fill it out. Through this, I could calculate the mean time between failure and the mean time to repair, which could then calculate the true availability of the process. This is my calculation sheets for determining the mean time between failure and the mean time to repair for all combined pieces of equipment. This is my measure phase of the project, in which I was calculating several data collection of scrap, defects, and downtime used in various quality indices and models. Current state of the process roll throughput yield was 78%. Later in the future, with all the improvements that had been completed, the roll throughput yield had increased to 98%, but I'm getting ahead of myself. This is my calculation that shows the logic that it's better to shut down the injection molding machine at each breakdown because we scrap more parts by continuing to run the machine. Shutting it down would be better. This is based on the amount of startup parts that were automatically rejected during a startup procedure over the number of parts scrapped over a 15-minute period for the same time. This is my analyze phase of the project. All indicators to me showed that the secondary equipment was experiencing failure pattern A, and it was now on the far left-hand side of that pattern to failure patterns B, C in the conditional probability of failure. I said about the restoration of the equipment, this is not to be confused with an overhaul, but rather to restore the equipment back from its suboptimal conditions. This led to quite a substantial undertaking, as you will see with the rest of this charter. As far as Six Sigma projects go, this is probably one of the biggest ones that I've done, with all improvements that need to be done from every department, from every piece of equipment. Every department had a piece of the pie in the improvement phase, such as myself in the continuous improvement department, quality, process, maintenance, setup, engineering, and operations. This is one of my Pareto charts for all the parts that are ran on the injection molding machine to date, with missing operation is the highest category for scrap. Another example of a Pareto chart for the same example. Through my mean time between failure and mean time to repair, I was also able to produce this Pareto chart showing how the downtime stacked up between the processes and which pieces of equipment were at the center of downtime. During the improved part of the charter, I would track downtime reasons by exporting the data from a computer maintenance management system and placing it in an Excel worksheet with a pivot table that I created to analyze stoppages. This is the improved phase of my project. Well over 100 improvements had to be done in order to fix this problem that I had discovered in the analyze phase of the project. This was the improved phase, corrective actions for the maintenance department. And what you can see here is just page 1 of 10. Part of the improvement phase, on many occasions, I had to produce 1-point lessons. This was just one example of a line stop authority showing the operators how to correctly shut down the injection molding machine if it started producing defects. Before this was instilled, the injection molding machine would continue to run because it was unattended, fully automatic, and would on occasion produce hundreds of scrap defect parts before a process technician could get around to shutting it down and investigate what was going on. In the charter for each improvement department, I had a countermeasure sheet to make sure nothing slips between the cracks. When someone misses a deadline or a milestone or an action item has been delayed for some reason, you capture it in the countermeasure with a PDCA cycle as to who's going to do what, by when, and follow up. Otherwise, everything starts to quickly fall apart if it's left to its own devices. This is the improvement phase, corrective actions for the injection molding machine maintenance department. Countermeasure sheet for the injection molding machine maintenance department. This is the improvement phase, corrective actions for the processing department. Countermeasures sheet for the injection molding machine processing department. This is the improvement phase, corrective actions for the molds tooling department. Countermeasures sheet for the injection molding machine tooling department. This is the control phase of the DMAIC process in my charted project. This is the control phase, corrective actions for the continuous improvement department, yours truly. This is a massive Six Sigma charted project for me, which took well over a year to fully complete. And I'm just scratching the surface on all that had to be done for the sake of presenting this to you in under 15 minutes. Like I said, there was no provision even for the most basic quality control practices were not in place. And I had to design and put in place red bin theory and train everyone how to use them. I could go very deep on the various things that I was working on with this project, with all the various processing. I was all over this process like strawberry jam, defining, measuring, analyzing, improving various deficiencies. And this is an example of my warpage studies to see what I could do to find out what was causing distortion in these SCR tank shells. The warpage was primarily a result of operating the process faster than it was originally PPAP to do, which didn't allow the parts to cool and set properly in the mold. I'll explain in the next few slides. I developed standard work on how to correctly handle defective pumps. Countermeasures at the sheet for continuous improvement department, yours truly. Now, I didn't use this control plan as part of this document because if it had been a design for Lean Six Sigma, I could see it being used as part of the PFMEA. Many moving parts in this project, and in my charter, I had a section tab in my Excel workbook to document and keep photographic evidence and links to outside control resources. The last tab on my Excel workbook was my charter. I had dedicated a sheet to house the embedded library documents and forms for ease of reference and access. This is my machine card, which shows that the PPAP sign-off for the Mercedes-Benz SR 167 was set at 138 seconds, and it was later reduced to 111 seconds to 98 later than that, with dire consequences. A difficult topic is cycle time. Many companies differ on their interpretation of what cycle time is to be considered. Cycle time reduction cannot override other efficiency considerations, especially when it comes to quality yield and machine uptime or availability. Part of these Lean Six Sigma projects is educating people. One of the greatest difficulties I had with this Six Sigma project was convincing the process engineers and technicians and senior management to understand the differences between a process delay and a lot delay, and how speeding up a machine does not necessarily mean a higher throughput when you take into account other factors. This for me was a classic case of confirmation bias, and they would not shift from their bias on cycle time. When I was due to present my initial findings of my project, I had already discovered that the increase of the cycle time produced more defects. This was a controversial subject. I had to convince them that they were just making defects faster, so I came up with this equation to demonstrate to everyone involved that when you factor in other inefficiencies, such as the case of, in this project, roll throughput yield and the availability of the equipment, this process was behaving like an actual cycle time of 176.19 seconds, not 111 or 98. This project was enormous, resulting in hundreds of corrective actions as part of the improve phase. Part of it was that I established line side and point of use storage for all the components. And this was a supermarket, and these containers are actually animal feeders, but they work great for this purpose. Thank you for watching. This is a series of videos that we will be producing each week to demonstrate my knowledge, skills, and how I've taken the methodology and deployed it. Please contact me at Fred Webberking at fred@fredwebberking.com. My mobile number is area code 864-283-1736. And of course, please do visit my online career portfolio website at fredwebberking.com. Thank you again. I am Fred Webberking. Bye for now.